Okay, so we've been talking about bonding in this chapter, and we sort of finished up talking about drawing Lewis structures. We also talked about bond energy, or bond enthalpy is sometimes referred to. So probably like kind of the only energy thing we're going to talk about in this class. A reminder that when we do sort of break bonds, it is endothermic, so heat and energy has to be put in. When we make bonds, it's exothermic, so we have to release that heat and energy, and exothermic, again, being negative in terms of those values. So really, when we're trying to figure out the enthalpy of the reaction or the heat of the reaction based on bond energy, remember that in a chemical reaction, really the only thing that happens is we essentially will break all the bonds on the reactant side and then pretty much make all the bonds on the product side. So really the way that we figure out the overall energy for that reaction is just to basically keep track of all the bonds we broke and how much energy is required to do that. And that will be sort of, again, positive values as it's endothermic. And then we add up all the bonds that we made, which would be negative. And again, whatever that end result is, whether it's positive or negative, when we add all those guys together, we'll tell you whether or not the reaction was endothermic or exothermic. Important when you do that, as we talked about last time, is to obviously know the type of bond that you're talking about. So if you're trying to break a double bond versus a single bond versus a triple bond, they will be different values. So you want to make sure that you look up on that table that we saw, which obviously would be provided for you for the correct one. So if you're not sure what it is or what it looks like, sometimes it's good to kind of quickly sketch out the Lewis structures for all those guys, and you could really just kind of visually see all the bonds. And sometimes that really helps a lot, especially sometimes the bonds in the middle. People oftentimes will miss those bonds, and you want to make sure you keep track of it. In addition, we also saw one, I think, or a couple there where the reaction did have coefficients, so you do have to take that into account when you're adding everything together and sort of subtracting everything together and keeping track of all that kind of stuff there. Any questions on that stuff we were talking about previously? Okay, so I believe this is where we sort of left off, talking about resonance structures. I think we got a little bit about it when we were drawing the Lewis structures. But basically, a resonance structure is really a set of Lewis structures where you essentially can draw, obviously, more than one structure. And the reason you usually can have that occur is in a structure where you do have something like a double bond that's there. And the double bond, for example, in several different ones, like carbonate, I think was one of the ones maybe we drew. You could have double bonded the oxygen on top, could have double bonded to the left, to the right, and you had sort of certain options as to where you could have put that double bond. And because you could draw more than one Lewis structure and they're all related to each other, they basically are what are known as resonance structures of each other. And as I might have mentioned a little bit ago when we talked about yesterday or the other day, that, you know, when you take something, for example, like carbonate, and if you remember, when we do make a double bond, we do bring those electrons in to do that. And those double bond electrons are delocalized, which means, again, at any given point in time, they could technically be like over here on that oxygen on the left. They then could kind of transfer and move around and, you know, end up with the oxygen up on top, or may end up on the oxygen on the other side. So those double bond electrons technically, you know, are kind of moving around from sort of one atom to the next. The real structure is probably somewhere between all those guys, all those kind of pictures that you can draw. So you could draw kind of three equivalent structures. They're equivalent of each other. And again, if you're not asked to draw the resonance structure, you literally could draw any one of the three structures and they would be perfectly fine. But again, usually if we draw resonance structures, we use this kind of two-headed arrow heading in those directions in between the different structures to indicate that they are obviously related to each other. So here's a couple of examples. Again, here's our ozone. We could have double bonded on the left. We could double bond on the right. The charges there are actually the formal charges that we talked about, and that also is something that we talked about last time, which was formal charge. And a reminder, when you calculate something like formal charge, You take the number of valence electrons in the free atom minus the number of non-bonding electrons minus 1/2 the number of bonding electrons. And again, you do something like that for ozone, as we see here. We had a -1 formal charge there on the oxygen, +1 on the center oxygen. Double bonded oxygen there has a 0 formal charge. And one sort of aspect of formal charge that we talked about last time is we could definitely use formal charge to help us decide between a better Lewis structure or between several Lewis structures, which one might be a better sort of arrangement to sort of choose from. But these, again, would both be resonance structures of each other. Again, essentially, for lack of a better description, you're just going to be basically moving that double bond to all the possibilities of where you could kind of move the double bond to draw any type of new Lewis structure or resonance structure. Here's carbonate, which I think is the one we were just talking about. And again, you can see you have basically 3 equivalent structures. Again, the minuses are the formal charges here, like we calculated earlier on each of those. And again, those are all equivalent structures. And as I mentioned, probably the true structure is someone between all 3 of those. The benzene ring looks something like this. It's like an organic molecule. Got 6 carbons. It's got a couple double bonds or 3 double bonds in there. The double bonds could actually move around to the other side. Looks something like this. By the way, each of these spots where a point is a carbon. These are all carbons, basically. And there's actually 2 hydrogens at each of those carbons all the way around. And if you take organic chemistry, which perhaps you're going to head that way, I'm sorry, but you'll probably head that way at some point, you'll learn to draw this a lot, benzene. And a lot of times what they'll do is you also see benzene just kind of drawn like this, or they're actually just put kind of like a little circle in the middle. And again, that implies that these double bond electrons basically are delocalized and they can move around. Could be on like the left-hand side, could be on the right-hand side. And again, that's a sort of a common shorthand for benzene that you sometimes will see drawn with that little circle to indicate that those 3 double bonds, again, you could have the resonance structures and they're moving around. And here's another set here where we have multiple options of moving our double bonds around. And obviously you could get a bunch of different structures depending on sort of what we drew. Don't worry about too much on that one, I don't think. All right, any questions on resonance structures? So again, our resonance structures, when you have an opportunity to draw more than one spot for that double bond, you could draw equivalent structures. And for our class, again, you don't have to draw all the resonance structures for anything unless obviously it tells you to do so. So if it doesn't tell you to do so, you just need to lay up pretty much a good Lewis structure would be probably sufficient. So we talked a lot about sort of the octet rule, and probably if you've taken the class before this, you talked a lot about the octet rule, and everybody always obeys the octet rule, and of course that's a lie. So here we're going to talk about some exceptions to the octet rule, and our exceptions to the octet rule, there's a couple or a few different exceptions. And one exception to the octet rule is the first one, which is what is referred to as a incomplete octet. And an incomplete octet basically means that there are less than 8 electrons around it. So there are certain elements that are perfectly fine with less than 8 around them. For example, beryllium hydride, which maybe doesn't really exist, but that has less than 8. As you can see there, it has 4 electrons around it. Very common one that comes a lot with the sort of incomplete octet is our boron. So boron is usually involved most of the time. Aluminum as well, but again, usually that's ionic bonding. So with boron is usually one that pops up a lot. And as you can see here, this is boron trifluoride, and it is perfectly fine with 6 electrons around it, as it has obviously 2 for each of these lines here. So 2, 4, and 6 electrons. And again, perfectly fine, not really looking for extra electrons in that case. Sometimes what is referred to, these guys that have an incomplete octet, they're thought of as being electron deficient, obviously. It actually makes them really good, something that you'll learn in 200B, It makes them really good Lewis acids, which means they're willing to accept those electrons because they're kind of short some electrons. So they're willing to do those type of things. So one exception to the octet rule that you come across occasionally is the incomplete octet, and I would say probably your boron guy is probably the one that you're going to see the most in that sort of arrangement of less than 8 electrons. Another exception to the octet rule is an odd number of electrons or odd electron molecules. And that is basically guys that when you count up the total number of valence electrons, you hit an odd number. So obviously if you have an odd number, that's going to result in somebody not having a pair of electrons. So here obviously one unpaired electron on each of these. So NO and NO2 are some examples of that. And it ends up with this sort of unpaired electron. There's sometimes what is referred to sort of as a free radical. Sometimes chlorine does that a lot in atmospheric chemistry, makes it really reactive. It's really reactive because it's only got one electron, so it kind of wants to fix that problem. So these things that typically have one unpaired electron are usually very sort of reactive, and they react very quickly a lot of times to try to, ultimately sort of correct that problem, try to get an extra electron and stuff like that. And again, probably in this class and in most classes, probably won't come across too many of the odd number of electrons, but again, it is an exception to the octet rule. And the third exception to the octet rule is the one that we talk a lot about in this class, and especially coming up here with some geometry we're going to be talking about, and that is the expanded octet. And the expanded octet is there are certain elements that are very happy to go beyond 8 electrons. They could go upwards of somewhere in the neighborhood of like 12 electrons around it. And that is basically what is known as an expanded octet. And pretty much if you look at a periodic table and you look right around where sulfur is, so you got sulfur, you got some chlorine, you got some phosphorus. So right here where sulfur is, and if you go kind of to the right of sulfur, to the left of sulfur, and down on the periodic table, those are the guys that have the ability to go over 8 electrons. So that guy right around sulfur in our non-metal region on the periodic table, sulfur, phosphorus, chlorine, and kind of down in our non-metal region, those guys have the ability to do the expanded octet. And the reason they have the ability to kind of do that is if you look at what period those guys are on, that is on the 3rd period of the periodic table. And on the 3rd period of the periodic table, that means n is equal to 3. And if you think about the orbitals that are there, when n equals 3, we have s orbitals, we have p orbitals, and on that 3rd energy level, that is where we first start to see our good friend, the d orbitals, first appear. Now, because these guys right around sulfur, and again to the right and left and down, because they have the d orbitals available to them, even if they're not using it, they have the ability to kind of stash all those extra electrons and go above 8 electrons. So that's why on the periodic table, if you look, those guys and down could do that because starting on the 3rd energy level, everybody below that will have d orbitals available to it. That also means that if you go above those guys on the periodic table, so if you go to where nitrogen, oxygen, fluorine is on the periodic table, that is in the 2nd energy level, n equals 2. And in the 2nd energy level, there's only s orbitals and p orbitals. These guys never have the ability to go over 8. They should always obey the octet rule because they don't have those d orbitals available to them. So definitely where nitrogen, oxygen, and those guys are in the 2nd period, they have to obey the octet rule. They cannot go over it. But those guys below it at sulfur and below, they can go above 8. And again, have that expanded octet because they have those d orbitals. SF6 is an example of that. So for example, sulfur there is 6, And we have 6 fluorines at 7. That's a lot of math there. We'll go with perhaps 48 and hope for the best. So if we do something like this, you would arrange it the same way, except that we have a couple of other guys, right? So here, and basically we would fill up everybody all the way around. I guess I really should have counted those there, but hopefully if we went all the way around here, we would have 6 times 8, which should hopefully get us to where we need, and we would fill it up. But again, our central atom here of our sulfur would have 2, 4, 6, 8, 10, and 12 electrons around it. And again, because it's sulfur, it has those d orbitals available to them, and it's perfectly fine to do that. Question on those 3 exceptions. So you obviously do need to know the 3 exceptions. You do need to be able to draw them, I suppose, if it happens. But I will say out of those 3, probably this again is the one that you will come across a lot in this class, is that expanded octet. Almost more than maybe the expanded octet, especially with geometry. So I know usually in the previous class they tell you never, ever, ever go over 8. But here, go over 8 a lot, probably in a lot of cases. It's okay. Any questions on that there? So let's take a look maybe at some here. Why don't you try, what we got? Let's try, why don't you draw XeF6? Why don't you do SbCl5? And let's do SeF4. So why don't you draw the Lewis structures for those, see what you come up with. Okay, let's take a look here and see how we're doing. So we'll start with the first one here. So we have xenon, which is group 8. So it's going to be 8 plus 6 times 7 for our fluorines. And when I corrected it here, I got my plus 2. So the plus 2 does mean I'm going to actually subtract 2 in that particular case. And that should give me something like 50 minus 2, if I'm not mistaken. And that should give me 48 electrons when it's all said and done in this particular case. So in this case, let's get rid of this guy here. So that's what I draw. We're going to go with the xenon in the middle. Remember, fluorine is the most electronegative, so it can't be in the middle. And logic tells us if I got one of something and a bunch of others, probably that one guy's in the middle. So you want to arrange your F's all the way around, just like we were doing the other day. And again, however you want to do it, it's fine. And you're going to do the same sort of approach. We're just going to make one single bond from the center to all the outside atoms. And again, that's going to now use 2, 4, 6, 8, 10, 12 electrons. That leaves me some more to go on the outside. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, and 36, if I'm not mistaken here. So I now have 1, 2, 3, 4, 5, 6 guys on the outside. They all have 8 around them, and 6 times 8 should be 48. So that is all my electrons that I have now put in there. Everybody outside has 2, 4, 6, 8. The center guy has 2, 4, 6, 8, 10, 12. It is okay for him to have 12 because, again, if you look on the periodic table, sulfur's here and xenon is below it, which definitely means it's got some d orbitals available to it to house all the extra electrons. Question on that Lewis structure there. Following sort of the same approach with this guy, we got antimony, which is Sb number 51 on the periodic table, and number 5 in terms of valence electrons, plus 5 times 7 for our chlorines. That's 35 and 5, which means our picture again here should have 40 valence electrons. Sb again going to be in the middle, as it is definitely lower in the periodic table than chlorine. And again, we only have 1 of those versus 5 of the others. So we will do our arrangement here. Doesn't really matter kind of where you put the 5th guy. But same idea, 1 bond to everybody. And that's going to give us 2, 4, 6, 8, 10 electrons. That gives us 30 more to go. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30 in this case. So we got 5 times 8, which is 40 total electrons distributed. Everybody on the outside has 8. Our Sb has 2, 4, 6, 8, 10. Again, Sb being below sulfur also has those d orbitals available to it. So it is perfectly fine in that arrangement. Question on those 2. All right, looking at the one I erased, which I think was SEF4, I think is the one I erased. And same idea here, selenium is group 6. So that's a 6 plus 4 times 7. That's 28, and 6 is a lot. How about 34 we'll go with? And that's going to be Se in the middle, fluorine on the outside in this case. Again, single bond to everybody. That is 2, 4, 6, 8. Filling up the outside, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. At this point, I have filled up all the outside ones, and I actually still have 2 more electrons. So just like we did with the other normal ones, they go on the center in pairs. So we just drop it right there on the center in pairs. That now gives us total 34 electrons all the way around, hopefully. And we have 2, 4, 6, 8 electrons for each of the fluorines. And our selenium there now has 2, 4, 6, 8, 10. And selenium on the periodic table right below sulfur. So also has those d orbitals available to them to house those extra electrons. Any questions on exceptions to the octet rule, expanded octets, how to draw them? Again, you still want to kind of follow the same sort of pattern. Usually should lead you to a pretty good structure that you need to do.
I had a question, Professor.
Yeah.
So you could never double bond those, right? Because like fluorine could never take that extra electron.
Exactly. So for example, fluorine there is in that period 2 on the periodic table, which means those guys are in the second energy level. So anybody there, fluorine, oxygen, nitrogen on that second level, doesn't have the d orbitals, so they must maintain basically the octet rule. They can never go over 8 for sure. So that's one thing for sure, they can't do that, yeah. So he can't lay up the double bond on that, otherwise he would have way too many. Other questions? Okay. Questions on, I think that's it for this chapter, believe it or not. Questions on Lewis structures, drawing Lewis structures, any of those things? Okay. So we talked a lot of the stuff in this chapter, bonding in general, electronegativity, bond polarity, drawing Lewis structures that obey the octet rule, ones that don't obey the octet rule, formal charge. Obviously, you need to be able to do all of those things correctly. Any questions on that? Okay, then we will roll to chapter 4 next. So just give me a second to boot it up. We'll kind of be continuing on with kind of the same idea. We're going to talk about everybody's favorite thing, which is geometry, right? And all that good stuff. So just give me a second here. that, hit that. Okay, so we're into chapter 4 here. Before we get too far, everything look okay on the screen there? It looks like the right size. Again, on my side, it all looks the same, so it doesn't look really small. Everything's good. All right, so in this chapter, we are going to talk about geometry and molecular geometry. We're going to talk about electron-pair geometry, molecular geometry. We'll also talk about some new stuff perhaps for you, which is hybridization. And we'll finish up talking about, I think, polarity and molecular polarity. So in the previous chapter, we talked mainly about bond polarity and using electronegativity to determine whether or not the individual bond between two atoms are polar or nonpolar. Here towards the end of this chapter, we're going to look at whether or not the entire molecule is polar or nonpolar with all its bonds involved. But first we're going to talk about geometry, and let us get into it. So molecular geometry does refer to really sort of the three-dimensional arrangement of the atom or molecule in space. And it does take into account a lot of the bonds that are present, the types of electrons that are present. The electrons themselves play a really big part in terms of the overall sort of geometries that we end up seeing with molecules. And it has to do with, as we will see here and talk about, the two really types of electrons that we've seen in Lewis structures. And those are either bonding electrons, which are obviously electrons involved in bonds, or whether or not they are just non-bonding electrons or lone pairs. And depending on whether or not you get like bonding electrons near bonding electrons, or lone pairs near lone pairs, or bonding near lone pairs, you get some different sort of effect. But the idea behind pretty much all of this sort of geometry is the idea that ultimately we have all these bonds in these molecules. They're all being held together by sharing of electrons. And the ultimate thing is electrons are negatively charged, which means just by the process of making all these bonds, we're going to get electrons near electrons. And ultimately, they really don't want to be near each other. So what they do is the best that they can to kind of get away from each other. And as they are sort of moving away from each other, as far as they can sort of manage in their particular arrangement, they will sort of lock into a certain three-dimensional geometry that obviously is what we're trying to talk about here and give the name. So we can sort of predict it, you know, from the Lewis structure that we sort of draw by looking really at the central atom. So whenever we do geometry, it is really the central atom that is the really important part to look at when you're applying geometry to a molecule. And as I mentioned before, the basis of all this is based on the fact that we are going to get these negatively charged electrons near other negatively charged electrons, and ultimately they are going to try to escape each other. But they can't completely escape each other, otherwise everybody would fall apart. But they do try to really spread out as far apart as they can. And especially, obviously, since we've been talking about bonding, it is those valence electrons that we're obviously talking about here. So the idea of sort of geometry here is what is sometimes referred to as VSEPR, which stands for valence shell electron-pair repulsion model, hence the abbreviation, because that is a long-winded word there. But it basically accounts for sort of the geometrical arrangements that we see in an atom. And when we talk about sort of geometry names, there's really kind of two geometry names that we do come across and we do talk about. And the first one is what is sometimes referred to as the electron-pair arrangement. So the electron-pair name or electron-pair arrangement name is one name, and what that describes is pretty much like what the title implies. It describes how the electrons are arranged in three-dimensional space around the central atom. Whatever electrons are there, bonding electrons, non-bonding electrons, how those electrons in three-dimensional space are arranged around that central atom. And then we also talk about another name, which is sometimes referred to as the molecular geometry. Or sometimes people just call this the shape of the molecule. And basically that describes, taking into account all the bonds that are there, the types of electrons, the overall shape, taking into account of the bonds and the whole molecule as a whole, what the shape is. Now, in certain cases, as we will see, and as you may perhaps remember, if you learned both of these names in the previous class, these names in certain cases will be the same name, and in certain cases, they will be some different names. And what's going to really determine whether or not there are the sort of the same name or different names is what's happening around the central atom. And they're really divided into sort of two compounds or categories. The first one is when you draw your Lewis structure or you have a molecule and you draw it, the central atom does not have any lone pairs or non-bonding electrons. So basically what that means is you drew your Lewis structure and there's no dots around the central atom. So no dots around the central atom means that there are no non-bonding electrons or lone pairs present. And that's one type of category that we deal with in terms of geometry. The other type is the opposite of that. You do have lone pairs or non-bonding electrons around the central atom. So when you draw your Lewis structure, you do see dots around the central atom. And as we will see, that is the point where these two names actually are different. When they have no non-bonding electrons, no dots on the central atom, both of those names are going to be the same. When we start to put in those dots around the central atom or those non-bonding electrons, that is when we really do start to see the differences in the names here. Now, when we're doing geometry, and really only when we're kind of doing geometry, there is sort of a very important rule to follow, and that rule is if you draw a double bond or a triple bond, both a double bond and a triple bond, when you see those guys and you're counting electrons and you're counting bonds, they count as one electron pair, even though it's a double bond or a triple bond, and it counts for the sake of geometry as only one bond. So that's a very important thing to keep in mind when you're doing geometry. Double bond, triple bond, when you count them, one electron pair and also one bond it represents. The last one, also sort of important, but not as extreme. And we talked about drawing resonance structures. So if you sort of drew a proper resonance structure, you could apply, obviously, this geometry to any of those guys. And in most cases, it will come out the same in terms of drawing those resonance structures and getting the right thing. All right. Just remember something I want to talk about. I know, it's a tangent. Let me tangent off here for a second. Before we get too far from what we were talking about at the end, so I'll just go to the beginning here. I knew there was something I kind of wanted to talk about. All right, let me just talk a little bit about the exception to the octet rule before we get too far into the geometry, and maybe explain why you sometimes will see a structure that you do commonly see. So let's take sulfate, for example, which is SO4 2-, and this is a very common one that most people sort of draw and come about. So if you draw sulfate here and look at sulfate, you got 6 plus 4 times 6 plus 2, that's 24, 26, 32 electrons. So one structure that you could draw for sulfate, which is very commonly done, is one that will look something like this. And that is obviously 32 electrons, and it's a structure that you can use, obviously, as the Lewis structure. But if you ever Googled it or looked at it, or maybe you've drawn it, you will sometimes see sulfate drawn like this. be drawn something like this with some double bonds happening. So now that we just talked about exceptions to octet rule, this is a perfectly fine structure for it. Sulfur can take all those electrons that are happening there. And again, we still have 32 electrons if we sort of go around it. So you may wonder, well, what is sort of the better structure or not the better structure? And just to tie in something we talked about last time as well, this is where we can use the formal charge to help us sort of determine that. So if we did the formal charge on this guy here for that single bonded oxygen, it would be 6 minus 6 minus 1/2 of 2, which is -1, which means all these guys are going to be the same. So we would have -1, -1, or 11 if you do too many scribbles there, -1, -1 on all those guys for the formal charge. If we did our sulfur in the middle there, there's single bonded sulfur, it would be 6 minus 0 minus 1/2 of 8, and that's going to give us +2. So this is the way that you would get sort of the structure if you followed all the single bonded rules and you ended up with all the electrons. Now, if we go over here to our double bonded guy and we do our oxygen with the single bond, it will come out the same as above. So these guys here would be -1. We do our double bonded oxygen, much like what we did last time. We would have 6 minus 4 minus 1/2 of 4. And that would be 0. And this guy would also be 0. And now if we did the sulfur in the middle with that exception to the octet rule, that expanded octet, looks like that, we would have 6 minus 0 minus 1/2 of 2, 4, 6, 8, 10, 12, which would give us 0. So this is very common how you see sulfate drawn, especially if you Google it. This is also sometimes how you would draw sulfate if you just kind of went through the rules. And based on formal charge, the one that would be better is the guy over here. And this guy would be the better one based on formal charge. We have zeros coming through here. We have -1 on the oxygens. We also have -1 on the oxygens here, but we do have a more larger formal charge, which is usually not the better sort of thing. So again, as we talked about last time, you can use something like formal charge to help you decide. And in the case of something like sulfate, actually going to the expanded octet technically gives you sort of a better structure than this single bonded one. They're both okay structures, but the one on the right would be a better structure based on that. And again, you can do that because that sulfur can handle that extra electrons. Question on that. I knew there was like one I wanted to do there. All right, so that was a throwback to way ago, like 10 minutes ago, and all that good stuff. All right, back to my non-tangent lecture here, perhaps. Let's see where we're at. All right. So we're going to talk about this geometry, and again, if you technically sort of apply your geometry to any sort of resonance structure, oftentimes it will sort of come out the same in terms of the geometry, as long as you drew sort of a legitimate Lewis structure for each of those guys. All right, so let us talk about, first off, the simplest geometry you could have. And the simplest geometry you could have is basically almost the simplest molecule you could have. And obviously the simplest molecule you could have is one where there's really only 2 atoms. So when you have a diatomic molecule, and that's basically just 2 atoms together, the only way you could basically arrange 2 things is a straight line, and the geometry will always be linear. No matter what it is, there is no central atom because there's really only 2 atoms involved. And that means that can be 2 guys that are the same. So both of these guys would have linear geometry. Could be 2 ones that are different. This would be linear. This would be linear. Could be 2 that have a double bond. This would be linear. Could be a triple bond, does not matter. The only thing that matters is there is just 2. So if you see anything that's basically a diatomic molecule, that is pretty much the simple one. You don't have to worry about anything. The geometry there is always going to be linear, no matter what it is. There's really only sort of one geometry for that, since there's not really a central atom, so linear just is the geometry that we have there, as we don't really have that central atom. So two of the same, two different, double bond, triple bond, doesn't matter. Only two, the geometry will always be linear. Now, if everything was that simple, that'd be great. We could go home, but unfortunately we can't. So if we have three or more atoms, we do need to look at a couple of other things. And when we do get three or more atoms, we do want to look at the central atom. So when there is a central atom, always the one that you want to look at. So first example here would be a central atom with two things bound to it. So that is BeCl2. This is an exception to the octet rule. It has only 4 electrons and is perfectly fine with it. And when we look at the central atom, which again is the important one here, and we count it, that is 1 electron pair there. That is 2 electron pairs. That also has 1 bond and 2 bonds. So something with 2 electron pairs, the electron pair geometry is linear. And something with 2 electron pairs and 2 bonds, the molecular geometry is also linear. What essentially happens is these bonding electrons here decide, I want to get as far away as I can from you. And they basically go on opposite sides of a straight line, and they end up on these sides of a straight line. And it has a bond angle of 180 degrees as we go across there. And again, both of these names that we're going to be talking about, electron pair geometry and molecular geometry, are the shape. They both are linear. So no non-bonding electrons on the central atom. Both of these names are the same. And basically because the only type of electrons we have interacting with each other are bonding electrons. So again, they're able to sort of escape as far apart as they can from each other and end up being 180 degrees and giving us linear. The next sort of geometry involves a central atom and 3 guys bonded to it. So boron trifluoride, again, is an example of this. And here, if we look at it, we have 1 electron pair, 2 electron pairs, 3 electron pairs. And we also have 1 bond, 2 bonds, and 3 bonds. So something with 3 electron pairs, the electron pair geometry name is trigonal planar. Sometimes people call this triangular. The molecular geometry name is also going to be trigonal planar here. And that is because it makes a 120 degree bond angle. It makes a nice, pretty, badly drawn triangle there, as I make it even worse by going over it a few times. But it makes a sort of equal triangle there, if I could draw straight. We got a nice little triangle happening there, 120 degrees apart from each other. Again, here, when we look at the central atom, there is no non-bonding electrons. So both of these names exactly the same here. And again, that's always going to be the case when you draw a Lewis structure and the non-bonding electrons on the central atom, there are none. You will always end up with the exact same name for both of those guys. It only gets different when you start getting some non-bonding electrons involved. So 3 electron pairs, trigonal planar, 3 bonds with 3 electron pairs, molecular geometry also going to be trigonal planar, again 3-dimensional, sort of a triangle type of shape is essentially what you got going on there. The next sort of geometry that we're going to see is one where we have a central atom and 4 guys attached to it. So CH4 is an example of that. And with CH4, again, if we look at the central atom, which is always the important one in geometry, 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. And again, 1 bond, 2 bonds, 3 bonds, and 4 bonds happening there. And something with 4 electron pairs, the electron pair geometry name is going to be tetrahedral. Tetrahedron, if you like older way of naming it. Most people go tetrahedral these days. And the molecular geometry name is also going to be tetrahedral. Again, no non-bonding electrons on the central atom. Both of these names, again, are the same here. Kind of like a triangle on the face of it, and almost sort of a pyramidal type shape on the bottom happening there. The bond angle here is 109.5 degrees between, like here. Any questions on those so far? These are probably some that you obviously have seen before in the previous class, but of course our new introduction of our wonderful exceptions to the octet rule, and especially our expanded octet, actually does give us some new geometries probably for most of you. So let's talk about the first sort of exception to the octet rule here and the geometry that goes with that, and that is a central atom that has 5 bonds to it. So a central atom with 5 bonds, something like PF5 here. And if we look at it, it has 1, 2, 3, 4, and 5 electron pairs. It also has 1, 2, 3, 4, 5 bonds. Obviously an exception to the octet rule, the expanded octet here. Something with 5 electron pairs has an electron pair name of trigonal bipyramidal. And it has a molecular geometry name, or shape, also of trigonal bipyramidal. Again, when we look at the central atom here, there are no dots on the central atom, so no non-bonding electrons. So again, our names are exactly the same. And the reason for that is it is essentially just bonding electrons near bonding electrons. So they're able to kind of spread out a little bit. We actually end up with 2 bond angles. Actually, this is triangular bipyramidal. I'm sorry. Got the trigonal in my head. I'll say with the right one there. So this is actually triangular bipyramidal on both of those. Should use the right terminology there. Triangular bipyramidal. Triangular because there is a bond angle that is 120 degrees, just like our triangle. You can see it right about there. Makes like a triangle, 120 degrees. And then we have our nice right angle at 90 degrees happening as well. So we have that right angle that's happening and our kind of triangle shape. So this guy actually has a couple of different bond angles happening. And again, the correct name really is triangular bipyramidal. It's got trigonal in my head, I think. And obviously we can go one more on this in terms of the expanded octet, and we could actually have 6 guys bonded to our central atom. And that also is an expanded octet, an exception to the octet rule. And this is a central atom with 6 things attached, like our SF6 we saw earlier. And in this case, again, we do have 1, 2, 3, 4, 5, 6 electron pairs. And we also have the 6 bonds, 3, 4, 5, and 6 bonds. So something with 6 electron pairs, electron pair geometry is known as octahedral. And the molecular geometry or shape, also going to be known as octahedral. Has a bond angle of 90 degrees. Got some, I'll just go with this one, kind of right angles happening there. 90 degrees happening in this guy. And again, no dots on the central atom, no non-bonding electrons. Both of these names are going to basically be the same. So a couple of new geometries that go with our expanded octet. And again, in addition to those, there's obviously ones with non-bonding electrons. Up until this point, in terms of the geometry that we've seen, both the electron pair geometry name and the molecular geometry name, again, as I said, are exactly the same. And they are exactly the same because there are no non-bonding electrons on the central atom. And what makes them the same is what that means, as I mentioned, only bonding electrons are there. So you have just bonding electrons near bonding electrons, you have atoms there. That is sort of the best situation for electrons when they're near each other. That's the most like I could almost manage. I'm still going to try to get away from you, but I'm not as want to get away from you as strong as I can because we're kind of the same. So the bonding electrons and bonding electrons will only allow the thing to move as far as they can. And since every electron pair there is a bond, they can only move so far. And both of these names remain the same. Now this does change once we start introducing non-bonding electrons on the central atom. When we introduce non-bonding electrons on the central atom, we will start to see a change in the name. And that is because when we introduce those non-bonding electrons, we actually get three different types of interactions that could occur. We could have what we have right now in those previous examples, which is bonding electrons near bonding electrons, which in terms of repulsiveness is the best situation. And the next sort of best situation, not getting so great, is when we have lone pair electrons near bonding electrons. For the lack of a better word, that's a Lewis structure where you got some dots near a line, basically. Yeah? So that is that situation right there. And when you have that situation, what's going to happen is because those are now non-bonding electrons, there's no atom sitting there. It has a little bit more flexibility, all the other guys that are bonded. So they actually can move a little bit more than they could when there's like a bond that's there. So when an extra bond is there, the atom that's there won't let them move as much. When we get rid of that extra bond and replace it with some dots or non-bonding electrons, that sort of frees up the molecule to move a little bit more. And the end result of that is the electron pair geometry stays the same. Because regardless if you have bonding electrons there or non-bonding electrons there, you still ultimately still have the same number of electrons there. But what does change is the molecular geometry or the shape of it. And that is because, as I mentioned, in a situation where we have four guys bonded, these guys can only move so far. And if we get rid of one of those bonds and replace them with some non-bonding electrons, these guys now could kind of move a little bit further because there's not this other bond up here on top that's kind of pulling it back the other way. So it has a little bit more room for movement. So the overall shape of the molecule, because of the lack of that extra bond and the existence of those non-bonding electrons, they're able to kind of move away from each other more. And they do want to move away from each other more because now we have non-bonding electrons near bonding electrons, and they want to get further away from each other because they're not very happy to be near each other in that sort of interaction. And they have the freedom to kind of do that a little bit more because we don't have that extra bond sort of locking everybody into place. So without it, they're able to move, and the name that gets affected is the shape of the molecule. The worst situation, as we will see, is when we actually get non-bonding electrons near non-bonding electrons. They absolutely hate to be near each other, and that's like when we get dots near dots around that central atom. And what's going to happen is they're going to try to go as far away as they can from each other. And as those guys go, so does the bonded atoms. They got to move as well, and the overall shape of it really starts to move because of that. So ultimately what we see happen is the actual overall shape of the molecule is actually what changes because of that lack of a bond, extra non-bonding electrons, extra incentive for everybody to move further away from each other and ultimately changing the shape of the molecule. But again, the electron pair geometry remains the same because you got 5 non-bonding electron pairs, 5 bonding electron pairs. They're still the same electron pairs around the central atom. Any questions on that there? All right, so let's take a look at an example here. First one here, we have a central atom, 2 things attached, and 1 pair of non-bonding electrons happening. And an example here would be SO2, which is sulfur dioxide. And if we look at this, again, the central atom here is the important one. It has 1 electron pair here. It has 2 electron pairs here, the dots. And now I have a double bond, and my double bond counts as only 1 electron pair. So this guy would have 3 electron pairs. Again, the double bond counts as only 1 for the sake of geometry. In terms of bonds, it has 1 bond here, which is our single bond, and our double bond also counts as just 1 bond. So it actually only has 2 bonds. So remember, double bond or triple bond counts as 1 electron pair and 1 bond. Now, because the electron pair geometry does not change, something with 3 electron pairs, as we saw earlier, is what is known as trigonal planar. But in this situation, we now have a couple of situations happening. We have bonding electrons near bonding electrons. We also now have non-bonding electrons near bonding electrons. And again, that's 2 very bad situations, and we're missing that 3rd bond. So now this guy can bend a little bit more, has a little bit more room to kind of spread out. And we end up with a molecular geometry that most people call angular. And I'll go with angular for this class. Some people sometimes will call it bent angular. But for this particular geometry, and we'll see something bent in a second here, you should have something to do with angular. It's usually the term that's sort of used with this one to describe this, this sort of geometry here. The bond angle and all bond angles really go with the electron pair geometry. So because we're lacking that 3rd bond like we normally would with our trigonal planar, it is going to be a little bit less than 120 degrees. Again, because with our 3rd bond there, we get that nice equilateral triangle at 120 degrees. Without that 3rd bond, like I just was talking about, it has a little bit more room to move. So the bond angle will be a little bit less than 120 degrees for that particular bond angle. Question on that one there. Next geometry is a central atom where we have 3 guys attached and 1 lone pair. And an example would be NH3. And NH3 here, 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. So this has got our 4 electron pairs. It also has, again, 1, 2, and 3 bonds happening. So same deal, our electron pair geometry name is going to be the same. So something with 4 electron pairs like we saw earlier, the electron pair geometry name will be tetrahedral. We have the same interaction happening here. We have bonding electrons near bonding, which is okay. We have non-bonding electrons near bonding, which is not so okay. In our normal tetrahedral, we have that 4th bond. Without that 4th bond, these guys can all kind of move away a little bit more. And we get a molecular geometry or shape of trigonal pyramid. And again, sort of makes a pyramid sort of shape on the bottom, sort of with that non-bonding electron, has that triangle type shape, and you get that trigonal pyramid shape. And you can see the bond angle is less than our normal tetrahedral of 109.5. In this particular example here, the bond angle is 107.3. So again, usually less than our normal tetrahedral bond angle of 109.5. And in Celsius, just in case you want to do temperature today. In this particular case here, 107.3 would be the bond angle here. As you can see, just slightly less than our tetrahedral. And again, it's because it's missing that extra bond. So everybody can kind of spread out a little bit more. Yeah, in terms of the bond angles, I'm a chemistry instructor, I think, so I should say yes to that question that you should know the bond angles, but I'm going to be honest with you. You should be familiar with them. I don't know if I'm going to ask you bond angles. Maybe it'll be like an extra credit question, like, you know, give me the bond angles when we take the test or something like that. So yes and no, but I'm not going to specifically probably ask you a direct bond angle question. But maybe it'll be like an extra credit type thing or something. So
I'm sorry, what's the 107 and which one's the 109?
The tetrahedral, where you have 4 electron pairs and 4 bonds, like we saw previous, the 4 and 4, so 4 electron pairs, 4 bonds, like CH4, that has a bond angle of 109.5, and that's your kind of classic tetrahedral arrangement because they're all bonded. With the lack of that 4th bond, like we have with the 4 electron pairs and 4 bonds, and we have the non-bonded electrons, in this case, they have a little bit more room for movement because it doesn't have that 4th bond kind of locking in place. And the NH3 here would have a bond angle of 107.3 specifically, which is less than 109.5. And so usually once you start sort of introducing non-bonding electrons on the central atom, sometimes when people ask about bond angles, they go, it's just less than the normal bond angle for that guy when there's all bonding electrons. So normal bond angle for something like tetrahedral is 109.5. It still has the 4 electron pairs, but not the 4 bonds. So it's able to move a little bit more. So usually they'll say it's less than 109.5. And in this specific example of ammonia, it's 107.3. Other questions on that? Before we move away from this, since we're talking about names and everything, let's talk about 2 names that are commonly used together, or shouldn't be used together. And that would be our good friend trigonal pyramid that we see here, and our other good friend that we saw earlier, trigonal planar. They are different. Yes, trigonal pyramid is 4 electron pairs and 3 bonds. Trigonal planar is 3 electron pairs and 3 bonds. They do mean different things. So if you have a question, you need to make sure you either write trigonal pyramid or trigonal planar. Don't do my favorite answer, trigonal, and that's it. Don't let me choose. I failed this class, so I'm going to get it wrong probably, yes? So you make sure that you choose. Or my other favorite answer for a question like that, this is trigonal. I'm very confident. That is clearly trigonal pyramid. I mean planar. Which was the right answer? I'm not really sure what that is. So make sure that you clearly choose correctly on those. They do mean the same thing. If you just lay up trigonal as your answer, it's not right. So you got to either go pyramid or planar. If it's one of those two, just don't lay up the trigonal and hope for the best. All right, words of caution there. Continuing on with our non-bonding electrons around our central atom. Our next one is a central atom with 2 things attached and 2 lone pairs around the central atom. And our good friend water meets this sort of standard here. And we got 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs here. We have only 1 bond and 2 bonds happening. So just like we saw before, something with 4 electron pairs, still going to have an electron pair geometry name of tetrahedral. Our molecular geometry name is going to be a little bit different here, and that is because we have all 3 electron interactions happening here. We have bonding electrons near bonding, we have non-bonding electrons near bonding electrons, and the worst interaction of them all, non-bonding electrons near non-bonding electrons. These guys near these guys, they definitely do not want to be near each other. So what ends up happening is one goes kind of this way, one goes this way to get as far as they can. And then obviously our bonded guys also start to move about as those electrons go this way, those guys go this way. And we get a shape that's known as bent or V-shaped. And the bond angle here would also be less than 109.5. which is our typical tetrahedral geometry, and it's less than 109.5. The actual number is right here, as you can see, 104.5 for water, and that's because of the two non-bonding electrons going as far as they can, and everybody else going this way. Now, this name here, and the one we started with SO2, this is the difference here. Bent or V-shaped implies this sort of geometry here, this bond angle of like 104, definitely less than 109. When you use that SO2 and angular, it is actually talking about something near less than 120, like 117, 116, something like that. So there is actually a difference between these two, and that's why, like I was talking about earlier, people usually use the word angular to imply this one, because again, it does mean something different in terms of the bond angle. So again, if you're going to use bent, you should probably use bent angular with this one, or just angular with this one that we saw earlier. Again, it implies a bond angle that is really different than the bond angle we typically associate over here with the bent or V-shaped. Any questions on that? So there is, again, a slight difference, obviously, in the bond angles of those guys, and I would recommend just using the, angular for the SO2 type of shape and the bent or V shape for the water type of shape. Any questions on that there? Okay, so let's then talk about, these are probably some of the ones you're familiar with still. We saw a couple of those expanded octet exceptions. We're now going to see some more geometries that are related to those, and these are going to be our expanded octets that have non-bonding electrons around them. So first example of that is going to be a central atom with two things bound to it and three lone pairs happening there. And in this particular case, if we count, we've got 1, 2, 3, 4, and 5 electron pairs happening. So this is 5 electron pairs. We got 1 and 2 bonds happening there. And because it has 5 electron pairs, the electron pair geometry name will remain the same. So something with 5 electron pairs is our triangular, I'll write it right this time, bipyramidal. But now we have all those really bad interactions happening. We have a lot of non-bonding electrons near non-bonding electrons, and they definitely want to get away from each other as they can. They almost make this kind of triangle shape as they escape each other. And what that ends up doing is making our bonded atoms really go to opposite ends. And the geometry of this guy ends up being linear. So the molecular geometry here ends up being linear in terms of its geometry. Basically, our two bonded guys end up on opposite sides of each other, while our lone pairs almost end up in sort of a triangle type shape. Bond angle here, actually linear bond angle, 180 degrees as it goes across that way. Basically, they spread out just like a straight old linear arrangement there. So 5 electron pairs gets us to our expanded octet. It's got 2 bonds, gives us our linear arrangement. The next expanded octet also going to end up with 5 electron pairs, but it's going to have 3 bonds happening. And if we look at this guy, a couple of things. We have around the central atom 1, 2, 3, 4, and 5 electron pairs. And we end up with 1, 2, 3 bonds. And in this particular case, what we end up with is an electron pair geometry, just like the previous one. 5 electron pair is going to be our triangular bipyramidal. And what ends up happening is our 2 non-bonding electrons really go away from each other. That means our 3 bonded guys ends up in this T shape, is what it's called. So the molecular geometry here is what is known as T-shaped. In this particular case, And again, bond angle would be similar to our triangular bipyramidal of like 90 degrees, as you can kind of see there, kind of bond angle happening as they kind of separate out in that particular case. And we have another one that has 5 electron pairs present and some bonds. So our next one will be something where we have a central atom with 5 electron pairs and 4 bonds attached. So if we look at that, SF4 is an example of that. And that is 5 electron pairs. So 1, 2, 3, 4, and 5 electron pairs. And our 1, 2, 3, and 4 bonds happening there. And something with the 5 electron pairs still going to be our triangular bipyramidal. So we got our non-bonding electron, our bonding electrons, and oddly, as you may be able to kind of see here, it makes like a seesaw type shape, and the molecular geometry going to be seesaw, 2 C's, E's. This is also sometimes, if you come across an older book or something, they sometimes will call this guy the distorted tetrahedral. Throwback name. Most people go with the seesaw, but you know, could be a Jeopardy question. You never know. So again, bond angle here related to our trigonal bipyramidal. You can see kind of the 120 sort of angle here with our non-bonding electrons and our 90-degree sort of angle happening as well. So a little less than that happening there. And again, you don't have to worry too much about the bond angles, I think. And that is our last one, I think, in terms of 5 electron pairs. So now we're going to move to our other exception to the octet rule, and that's the expanded octet that has 6 electron pairs around it. So our next one here with 6 electron pairs, we have 4 bonds to it and 2 lone pairs around the central atom. So this guy here, 1, 2, 3, 4, 5, and 6 electron pairs. And has our 4 bonds, as we could see here. And this with 6 electron pairs, going to have the same electron pair geometry as our other one with 6 electron pairs, and that is our octahedral in terms of the electron pair geometry. Again, here we have our non-bonding electrons. Looks like he's standing on his head here, but our non-bonding electrons trying to get away as far as possible. And they actually end up making this guy into a square, the bonded guys, that's in the same plane, hence the name square planar. This square ends up being within the same plane of the molecule, and the molecular geometry here going to be square planar. Not to be confused with trigonal planar, which is different. So square planar, much like the name implies, makes more of a square. As we saw earlier, our trigonal planar makes more of a triangle type shape. Bond angle here about 90-ish degrees there in the square. And we got, I think, one more geometry here to go, also having our 6 electron pairs around the central atom. And this is going to be something BRF5. If we do this guy here. And again, if we count it up here, 1, 2, 3, 4, 5, and 6 electron pairs. Only 5 bonds happening here. I guess only is one way to say that. And that gives us our electron pair geometry of also octahedral because there is 6 electron pairs. Again, with just the 1 non-bonding electron and our sort of 5 bonds happening here. Again, you can kind of see it, almost a square and also almost this pyramidal type shape that's occurring in sort of 3-dimensional space. And the molecular geometry here going to be square pyramidal. And again, the bond angle here also going to have just a little bit less than perhaps 90 degrees in this particular case based off of the octahedral arrangement. So some of these geometries you probably remember, some of these new ones you just learned probably. And again, it has to do with our expanded octet, which we have those other geometries. So clearly you do need to be able to identify all the way through here, draw the Lewis structure, identify the electron pair geometry and the molecular geometry. Truthfully, most of us cannot visualize in three-dimensional space, myself included. So usually the best way to do it is to memorize electron pairs, bonds, and the names that go with it is usually the best way to do it. Here's sort of a table, I think, of all the ones that we sort of talked about. You have a similar one in there as well. Did I write only 4 bonds? It is a typo, thank you. I got it right there. I wasn't counting very, thank you. That should be 5 bonds. Yep. You don't want to put this on Tuesday's exam? I mean, really? No? We're going to put all this on Tuesday's exam. Everybody, let's all drop together. We'll just drop the class together. No, I'm just kidding. No, this is not on Tuesday's exam. So a reminder, Tuesday's exam is just exam one. It is exam 1, but it's chapter 1 and chapter 2. And again, the only thing for chapter 3 that you need to know about, as we talked about, was the electronegativity trend and stuff like that. So the bonding and all that stuff that we started, the rest of chapter 3 will be on exam 2, along with this, obviously. So here's just a table. You have a similar one in your book. Again, you can see that when we start putting those non-bonding electrons in there, our bond angles get a little bit less than what they were in their kind of normal arrangement. And we also start to see some differences in both of those names. And here's our other guys here. And again, you can see here a square planar 90 degrees, and then also this guy, the last one we finished up on, a little less than 90 degrees. Again, they usually typically, like we've been talking about, get a little less than that 90 degrees because they are missing sort of at least one bond, and they got those non-bonding electrons, again, giving a little bit more flexibility and a chance to get away from each other a little bit more. And that's how come we get these sort of bond angles that are a little bit different. All right, well, that is enough to digest, I suppose, for tonight. Any questions on any of those things? Obviously, you do need to know those. This chart or anything like that will not be provided for you, so you do need to obviously know all those things. All right, any questions on any of that? So as sort of the question asks, a reminder, right, the exam will be Tuesday, this coming Tuesday, and it will again be on chapter 1, chapter 2, and like I said, just what electronegativity is and the general trend on the periodic table from chapter 3. We will have lecture on Tuesday like normal. We might stop a little bit early, but we'll do a little bit of lecturing just to keep on pace. And then on during lab time, I think we're going to take the exam during lab time. So you'll just go take the exam. I think it will probably be using Proctoral like we did the quiz, and you'll take it at the start. It will open up at the start of lab, and you can take it. It'll be kind of the same sort of format. There'll be some problems where you have to work out and upload. You'll work, and then there'll be just some straight old multiple choice questions that you don't have to actually show any work for, just kind of yes or no, right or wrong type deal. And then there'll be kind of like a written part where you'll show some work and upload it and get partial credit for. Any questions on any of that? A reminder that you'll be given a periodic table. You'll be given